Hi everybody, my name is Melissa Graff, and for my final project I investigated the relationship between citizen science volunteer behavior and spatial trends in the data that they collect. Citizen science is by no means a new concept, but the past 2 decades have seen a significant jump in public participation within scientific research. Through virtual and mobile platforms, more people than ever have the ability to participate in modern research projects. Relying on volunteers is not only a cost-effective method of collecting data, but it is incredibly common within science. In a sample of 503 projects, 17% of them were found to incorporate data that was collected by citizen volunteers. These data are used for a wide variety of purposes, including monitoring the long-term population trend of a species, as well as providing invaluable resources for conservation action plans. Virtual citizen science projects are unstructured by nature. They are flexible, have few requirements for data input, and allow volunteers to record observations as they happen. None of these things are necessarily bad on their own. The fact that people are able to participate on their own terms is an attractive feature that contributes to its appeal to a wide audience. However, because these data are becoming more and more common within research projects, it is important to understand whether sacrificing rigorous standards of data collection for the sake of public appeal negatively impacts the data and, subsequently, the studies which rely on them. Due to the opportunistic nature of citizen science data, spatial and temporal biases are not uncommon. This occurs for a number of reasons, including causes related to the structure of the project, such as loose data requirements, as well as reasons related to the volunteers themselves, including variations in the amount of effort expended per observation, the amount of land covered, and differences in volunteer ability to identify species. Additionally, previous studies have shown that the characteristics of the physical environment affect whether a volunteer is likely to try to collect observations in a particular area. The more rugged and less appealing the landscape, the less likely a person is to try to traverse it. In order to investigate the potential spatial biases present in virtual citizen science data, and to examine these biases in relation to volunteer behavior and motivations, I chose to take observational data collected on monarch butterflies between the years of 2016 and 2019 and characterize them based on multiple factors, including land cover type and proximity to populated urban areas. To do so, a series of visualizations comprehensively displaying where people tend to collect data was created. Ultimately, through this project, I hoped to gain insight into how patterns of volunteer behavior affected the spatial distribution of observations. Additionally, I wanted to use this as an opportunity to talk about how these biases may affect the studies that use these datasets, as well as what some projects are doing to try to mitigate this. Monarch observations were obtained from Journey North, a project that has been collecting data on monarchs and other pollinators since 1997. Shapefiles were obtained from the Iowa Geodatabase, the Iowa Department of Transportation, and the United States Census Bureau. Because of its status as primarily an agricultural state, Iowa has a surfeit of websites and organizations dedicated towards collecting geospatial data and information. Iowa in particular was chosen because it holds significance for pollinators. Despite the fact that, today, it is largely farmland, it was historically a prairie state. The shift from prairie to farmland and the increased use of herbicides has led to declines in the monarch population. But there are many initiatives aimed towards restoring vital pollinator habitat, including strips, also known as the science-based trials of row crops integrated with prairie strips. This program is focused on incorporating native prairie plants into agricultural fields in the hopes of establishing habitat for pollinators and other native species. The data on monarch observations were taken and read into Program R, filtered by only observations located in Iowa, assigned unique identifiers, and stored in a database using SQLite. From there, the database was imported into ArcGIS Pro for geospatial processing and visualization. Using the land cover types as classified by the Iowa Geodatabase, as well as the Iowa Department of Transportation, the land was broken into 4 generalized categories: cities, populated rural areas surrounding cities, agricultural land, and outdoor recreation/wildlife management areas. This map makes it easier to see just how much of Iowa is dedicated towards agriculture. The brown/tan areas on the map are all farm fields. Most of the state is completely overtaken by agriculture, with a few cities and rural areas, and only just a tiny amount of land set aside for wildlife management. This map is more or less the same as the map we just saw, but with the 134 monarch observations overlaid on top of it. This is the quote-unquote raw observational data layer before it was split up into the 4 land categories. The first step in characterizing each observational point by land type was to perform a spatial join between the observations layer and each land cover layer. This allowed me to tally up the number of observations that overlapped each of the 4 land cover types. In total, there were 46 located within cities, 11 located in rural areas, 14 located in recreational/wildlife management areas, and 59 located in agricultural lands. In order to see the effect that proximity to urban centers has on observations, I created a map with a 2-mile buffer surrounding cities in Iowa, and then spatially joined this layer with the layer containing all Monarch observations. This resulted in a map that contained 105 observations, which is 78% of all of the observations that were recorded during the study period. As you can see here, this is the kernel density map that was developed. This map is actually quite peculiar at first glance. We can see that the highest values tend to be correlated with the larger cities. We can see a dense cluster in the Des Moines and Cedar Rapids areas. However, when we look at the southwest corner of the state, near Red Oak, there's an incredibly dense clustering of values. This is due to the fact that, in just this small area, there were 31 Monarch observations collected during the study period. In other words, 23% of all observations are located here. This actually raises some interesting questions. Throughout the entire state, are the areas without any observations truly lacking the presence of any monarchs? Or is this indicative of the effect that variable levels of volunteer effort and differences in the number of active volunteers can have on the number of observations within a dataset? At 44%, agriculture holds the highest percentage of monarch observations throughout the study period. However, when we take into account what we learned from the buffer map as well as the kernel density map, we know that, despite being located in agricultural land, the vast majority of all observations were located within 2 miles of city limits. In other words, most of the observations were recorded near populated areas, close to where people live. This makes sense. There have been studies that have shown a correlation between the attractiveness of the surrounding landscape and volunteer behavior. The more rugged or inaccessible the area, the less likely volunteers are to try to traverse it. It is not outside the realm of possibility that the reason there are higher numbers of monarchs recorded near cities, rather than scattered throughout the state more evenly, is because it is much more convenient for people to record observations in the areas where they already plan to spend time. There are large swaths of agricultural land, particularly in the northwestern portion of the state, where there are few, if any, recorded observations. These areas lack proximity to major cities, likely featuring a much lower number of active volunteers. All of this serves to draw attention to one of the flaws in this type of unstructured dataset: the lack of information regarding the survey methods employed by volunteers. Because many citizen science datasets do not require volunteers to record information regarding the areas where they recorded their observations, we have no way of knowing how many of the areas that do not have any observations have been surveyed by volunteers. Because of this lack of information, many virtual citizen science datasets are not suitable for population monitoring or generating species distribution models. However, there are a few methods that can be employed to combat this problem. Trying to maintain the flexibility of a citizen science platform while requiring a certain amount of additional user input is not an easy task. Luckily, there are platforms which are attempting to tackle this challenge. Let's take a look at eBird, which is a bird monitoring app managed by the Cornell Lab of Ornithology. Like other virtual citizen science platforms, such as iNaturalist or Journey North, eBird allows users to input observational data regarding the number and species of birds that they have seen. In addition to this, eBird requires users to answer a few extra questions about their surveying process, including whether the volunteer was stationary or covering a certain area. If they were moving, it asks how far of a distance was traveled. Whether or not the sighting was incidental, the duration of the observation, when it started, how long it lasted, and when it ended, and how many people were in the birding party. The user is also asked to input any additional information that would be helpful to the researchers. Incorporating simple questions such as these, while it requires more involvement from the user, ultimately results in higher data quality, as it provides researchers with valuable information regarding the surveying process. While eBird's methodology is incredibly useful, unfortunately, it is one of few platforms which asks these questions of its users. Fortunately, however, research has been conducted into models that can be developed that take sampling bias into account, even without information on the surveying process. A study conducted in 2013 investigated whether occupancy models can offset the lack of standardized protocol in volunteer sampling methods. Occupancy models rely on detection/non-detection data, producing an estimate of the percentage of sites that are occupied per year. They found that, when comparing observational data of butterflies and dragonflies from standard monitoring data with opportunistic data that had been corrected for, the two datasets were fairly evenly matched. However, this study focused on sampling sites that were 1 by 1 square kilometers where opportunistic sightings had been recorded. With this in mind, it is unclear whether this method could be expanded into an area where the number of sampling sites and the number of times that they have been visited by volunteers is unknown. Regardless, this is a method that can be used in certain situations to reduce the issues caused by volunteer sampling biases. Through this project, I wanted to investigate the potential spatial biases that exist in virtual citizen science datasets, particularly concerning monarch butterflies in the state of Iowa. In doing so, the connection between relative proximity to urban centers and the number of monarch observations was discovered. This demonstrates both the tendency of volunteers to perform observations in areas that are convenient or appealing to them, as well as the fact that, without information regarding the methods that volunteers employ during their observations, we are still lacking in crucial data. In order to increase the amount of high-quality data that can be collected through virtual citizen science projects, these platforms should consider incorporating methods that allow the user to include this information alongside their observations. If these measures are not taken, the data can be coerced into a useful format through statistical methods, such as occupancy models. While citizen science datasets that rely on opportunistic observations are far from perfect, they are still an invaluable part of data collection in modern scientific research. By understanding where they fall short, we are able to construct a clear picture of how to move forward, and ways that we can continue to improve this field and continue to make science accessible to everybody. I hope that you enjoyed learning about my project. I love to talk about and participate in citizen science, and I hope that this project sheds some light on its benefits, as well as the areas where it can be improved. Let me know your thoughts, and thank you so much for watching.